In this video, we will prove that the rationals are countable. So we'll actually tackle a slightly weaker form of this. Let's show that the positive rationals, which we can denote as Q plus, are countable. So remember that rational numbers are numbers that can be written in the form a over b, so as fractions, where the a and the b are integers. And of course, b can't be 0, otherwise it's undefined. So remember our key idea from before. To show something is countable, we need to show that we can list out its elements in a sequential way, in a systematic way. So these blank spaces will indicate, some rational, hopefully, that I can fill in. And I want to show that if I keep going like this, there's some systematic way to list all of the positive rationals. Because if I can do that, then that means I can form a bijection from the positive integers to each of these positive rationals. So how are we going to systematically list them? Okay, this is where this grid comes in. So this grid, the way I read it is, this first row represents all the positive rationals where the numerator is 1. The second row indicates all the positive rationals where the numerator is 2, and so on as I go down this. And this grid keeps on going to the right, it keeps on going down, so it will have all the positive rationals. In fact, it repeats some of them, like 1/2 and 2/4 and 3/6. They're showing up multiple times. So we'll talk about how we're going to deal with those repeats as well. So here's how I'm going to list them systematically. Let's start with the top left corner, the 1/1. After that, I'm going to go down to the 2/1. From there, I'm going to snake up this diagonal, snake up that diagonal, hop on over, snake down this diagonal, hop on down, snake up, and then over, and then snake down, and I'm going to keep going along diagonals like this. Okay, so from here, I'll go to 1/2, then I'll go to the next diagonal, 1/3, then to the 2/2, but that's the same as 1/1, so I'll skip that. I don't want to list it twice. Then I go to 3/1, then I move myself to the next diagonal, so to 4/1, then to 3/2, then to 2/3, then to 1/4, then I hop over the next diagonal to the 1/5, and I would keep going. I would go down this diagonal, go to the next, and then up the diagonal, and keep continuing in that way. All right, so what we are doing here is we are snaking through these diagonals, snaking through the diagonals in this grid, and when we do that, we will skip rationals that were already listed. So if I encounter the same rational again, like a duplicate, like I did with 1/1 and 2/2, well, I skip it the second time. Okay, so I'm ready to describe this in terms of my bijection, which I'll call f. So I'm going to take the first positive integer, and I'm going to map it to the first thing in this list, to 1/1. Then the second positive integer will map to the second thing in the list, which is 2/1. And then f of 3 will be the third thing, which was 1/2. And f of 4 will be the next thing, which was 1/3. And f of 5 will be 3/1, right? Because I skipped the 2/2. And ... We keep going like this. And this gives a sketch of why the positive rationals are countable, why I can list them. This is not a formal proof because my function f, my bijection, is defined rather imprecisely. But nonetheless, I think this sketch gives us a good visual sense of why these are countable. Okay, so it turns out that if we look at all the rationals, they are countable, and I'll sketch a proof of why that is. So we know at this point that the positive rationals are countable. So they can fit into Hilbert's hotel. That was the hotel from the first video in this section that has an infinite number of rooms. Positive rationals can fit in it. The negative rationals would represent a countably infinite bus that shows up. So a bus that has a countably infinite number of passengers. Well, we can fit them into the hotel like we did in the first video. And I'll link that below so you can refer back to it. The only thing left would be the number 0. And we can fit that in as well, but I'm going to leave that for you to think about. Like, what would we do to the already full hotel to adjust the people in it to fit in this extra number 0. So at this point, we have established a number of examples of countable sets. We've started with z plus, the positive integers. We had the non-negative integers, z greater than or equal to 0. And then we had all the integers. They were still countable. And as we saw in this video, the positive rationals, as well as all the rationals, those are all examples of countable sets. Even though seemingly they're getting bigger and bigger and bigger, but they're all actually the same size. They have the same cardinality. And at this point, we might wonder, well, are all infinite sets, are they all countable? And that's where the reals come in, and they say, hold my beer. Because we'll show in the next video that the reals are actually uncountable.